Not seeing any questions.
This meeting is being recorded.
Not seeing any questions, then today we're going to be starting a new topic, which is basically entanglement in quantum field theory. And the basic result about entanglement in quantum field theory is something called the Riesz-Leiter theorem. Which makes a claim that at first sounds completely outlandish. It says that, it's usually formulated just in Minkowski space. So for today, we'll be in Minkowski space. It really is applicable in any space-time. First of all, in Minkowski space, if you take a field operator, so a sequence of field operators acting on the vacuum can create any state in Hilbert space, roughly speaking. Well, there are two caveats about any state. First, any only means really only a dense set. As long as you only act on the vacuum with finite many field operators, you can only approximate a quantum state, because the quantum state, for example, in free field theory, might have an arbitrarily large number of particles with very small probability. So states obtained by acting on the vacuum with finitely many field operators will only approximate such a state. So any state really means any dense set. So any really means a dense set of states. And secondly, any means any in a superselection sector. So if we have a theory with electric or magnetic charge, our gauge invariant local operators won't carry electric or magnetic charge, so we only will produce the neutral states. But in quantum field theory, you can practically take this as an axiom. A sequence of field operators acting in the vacuum will create at least a dense set of states in a superselection sector in Hilbert space. If you look in the book by Streeter and Witten on quantum field theory, this is literally an axiom. Now, the Riesz-Leiter theorem says the following, which is surprising. So here's Minkowski space, and here's U. U is an open set in Minkowski space. It says that even if we restrict all the points to be in U, a sequence of field operators in U acting on the vacuum, omega is the vacuum in case I wasn't clear enough, is still a dense set of states. That's surprising because, for example, in an appropriate quantum field theory, let's say that the moon is described by this theory. And so we could have a state that has the moon located far away from you, from region U. So that sounds at first sight like a state you couldn't possibly create by acting with field operators in U. But the Riesz-Leiter theorem says that any state, and in particular this one, can be approximated by states that you make by acting with a finite set of field operators in region U. So how are we going to prove that? So I might say, I'm taking my generic quantum field to be a scalar field phi. The structure of the argument is such that it wouldn't matter how many quantum fields we had and how many quantum fields we needed to generate the operator algebra of a given theory. Just for simplicity in notation, we assume that one is enough. Well, if this is false, then there exists some state chi that is orthogonal to all the states as long as the points xi are all in the region U. In other words, the states that you can make this way are at any rate a linear space of states. And if this space isn't dense, there's something which is orthogonal to the Hilbert space closure of all those states. If the Hilbert's dense would mean that the Hilbert space closure of all these states is all of Hilbert space. Not dense means that it's a proper subspace. If it's a proper subspace, then there's some chi orthogonal to that proper subspace. So if the statement is false, there's some chi that's orthogonal to all these states. So with that in mind, we define this function f of x1 up to xn is the inner product of chi with phi of x1 up to xn. And chi, by hypothesis, has the property that f vanishes if all the points from x1 up to xn are in the region U. That's the statement that chi is orthogonal to all the states you make by acting with field operators in U. So, well, we want to show that there's no such chi, but we'll show that if it's true that f vanishes whenever the x's are in region U, that this implies that f is identically 0 for all choices of the x's. But that will imply that chi is 0. Because our axiom for quantum field theory said that field operators acting on the vacuum are dense, at least in the superselection sector of Hilbert space. And therefore, any chi that's orthogonal to all those states has to be 0. So the idea of the proof of Riesz-Leiter, or the goal will be to prove that this function, if we know that this function vanishes when the x's are in a given open set, then we'll show that it vanishes altogether. Are there any questions so far? Okay, so we're going to first show that we can move the last point out of region U, and f still vanishes. But even for the, so first we pick, there will be 2 steps. Pick a time-like direction. I guess I should say a future-directed time-like vector t. And we're going to consider shifting xn to xn plus ut, where u is real. So we'll consider this function where you replace xn by xn plus ut. In other words, we'll look at this. So I want to prove that this vanishes for all real u. So at least xn can be moved out of the open set it started with if we move it in a time-like direction. Well, this function has 2, I regard it as a function of u keeping the x's fixed. This function g of u has 2 properties. The first, g of u is 0 if U is real and small. Because if U is sufficiently small, then shifting xn to xn plus ut doesn't move xn out of the open set curly U. Second, we can do the following. Phi of xn plus ut is e to the iu h, phi of xn, e to the minus iu h, where h is the Hamiltonian associated with the particular time-like vector t. So G of U can be written like so. Now we're going to use two facts. One is that the Hamiltonian annihilates the vacuum. And the second is that the Hamiltonian is non-negative. And of course, the third fact we'll use is that this is true in all Lorentz frames. So since the Hamiltonian annihilates the vacuum, I can throw this away. And because the Hamiltonian is non-negative, G of U is holomorphic in the upper half U plane. So we have a function G of U with two properties. Well, initially it was defined for real U. Okay, was it obvious why it's holomorphic for positive, for imaginary U positive? H only has positive values. It was important that we got rid of this e to the minus iuh. That would have favored continuation to the negative imaginary part of U plane. But because H annihilates the vacuum, we got rid of that factor. Once we got rid of it, we see that if U has a positive imaginary part, since H only has positive values, this will be exponentially decaying. So we have a function that's holomorphic in the upper half plane and vanishes one part of the real axis. If we knew that G of U was holomorphic on the part of the real axis where it vanishes, we'd trivially say that it's identically zero, because a holomorphic function that vanishes on part of the real axis is identically zero. For example, you know that holomorphic functions have power series that converge at least locally. And if the function is zero on the part of the real axis, the power series around a point there is zero. To begin with, we don't know that G is holomorphic on any part of the real axis, only that it's holomorphic above the real axis. But that's actually good enough, as you can see as follows. At a point where the imaginary U is positive, we could write a Cauchy integral formula. So for U in the upper half plane, we can say that G of U is an integral over gamma to U prime, G of U prime over U prime minus U. And then we can move, obviously, well, G is continuous up to the real axis where we defined it to begin with. So we can take the limit that part of the contour is actually on the real U axis. But since U vanishes there, we could erase that part of the contour. Oops, I erased too much. So now we're defining G of U by a formula like this, with an open contour that has a missing part on the axis. And in that representation, it's manifest that we have holomorphy if we move u to the axis and even into the lower half plane. So in particular, we learned that such a g of u is actually holomorphic on the real axis. And since it vanishes there, it follows that g is identically 0. So we've learned the following. What we called t was any time-like vector. So we move the point xn in time-like directions from u. So we learned that you see, replace xn by xn plus ut. But that could be anywhere that's time-like separated from where we started. So there's now a huge set where xn could be, and this function would still vanish. But it's not all of Minkowski space because it doesn't include points that are space-like separated from u. So how would we extend the argument to get points space-like separated from u? Well, we just make the same argument again. We pick a second future-directed time-like vector t prime. And now we replace xn plus ut by xn plus ut plus u prime t prime. So now we look at this new shifted function as a function of u prime. Well, we make exactly the same argument as before. H of u prime is 0 for small real u prime. Because if u prime is small enough, this shift leaves a point that's time-like separated from u. And by the same logic as before, it's holomorphic for mu prime positive. Therefore, h of u prime is identically 0. But now you see, starting in u, going forwards by one time-like vector, and then going possibly backwards by another time-like vector, we get anywhere. So xn plus ut plus u prime t prime is any point in Minkowski space. So at this point, at this moment, we've proved that this is 0. F is 0 if x1 up to xn minus 1 are in u with no condition on xn. So any question on how we learned that?
Do we need to assume relativity here,
Oh,
like the Hamilton?
Well, I told you, okay. We had to use the fact that the Hamiltonian is bounded below and annihilates the vacuum in all Lorentz frames. Although really, it would have been enough to know this in at least 2 Lorentz frames. But you see, in ordinary quantum mechanics, these would be sensible conditions in in one coordinate system, but not in two. So in practice, the power, two Lorentz frames was enough because we only use two time-like vectors, t and t prime. But it's extremely artificial for these conditions to be true in two distinct Lorentz frames, except in a relativistic theory. Good luck in finding a theory that isn't relativistic where these properties would hold.
I see. Thanks.
Sure. Any other questions?
I've got a question.
Yes.
When you choose t prime to be not future pointing, so when
No,
it's
no, t
past
prime,
pointing,
well, if it
do we have a problem that h is then not positive?
Well, two remarks. First of all, since u is allowed to be negative, it doesn't matter whether t is future pointing or past pointing. The only reason I specified whether I shifted xn by ut and both signs of u are allowed. So there was no loss of generality in assuming t was future pointing.
Okay.
However, if I'd said that t was past pointing, I would have made the same argument using the lower half plane instead of the upper half plane. The only reason I specified t was future pointing was to know which half plane to talk about. Either way, we were going to get holomorphy in one half plane. Is that clear?
Why do we know that the function is 0 for u in the lower half plane when we don't know that it's holomorphic there?
You're asking if t is past pointing, how do we get holomorphy in the lower half plane? If t had been past pointing, then the corresponding h. If t is future pointing, I defined h here. If t is future pointing, that formula defines an h which is bounded below by 0. If t had been past pointing, that formula would have selected an h that's bounded above by 0. So the Hamiltonian that generates translations in a past direction would have been negative, would have negative eigenvalues. If you find that confusing, let me suggest you stick to the future directed case. It should be obvious, though, that since we allowed both signs of u, it can't matter whether t is future directed or past directed. Right?
Okay, thanks.
Sure. Any other questions?
I have some confusion.
Yes.
So when you choose after you do it for every u and then you choose the u prime, aren't you already out of the region that was open in the beginning?
Well, no. One way to say it is that if u prime is small, that is equivalent to shifting xn in the original region. So we had vanishing for xn in the original region in any u. Shifting u prime would have left xn in the original region.
Yeah, my confusion is about point A. Is it true for any u or only for small u?
It's only true for small u. Small u.
Okay. No, not u prime, u.
Oh, no, it's true for any u and small u prime. This is true for any xn and u. Well, let's see. When u prime is 0, we had vanishing for any point that was time-like separated from where we started. And for small u prime, we're still time-like separated from there. That's one way to say it. Another way to say it, which is the way I said it originally, is that if u prime is sufficiently small, you could think of that as a small change in xn that keeps xn in the original region curly u.
Yeah, okay, thank you.
But more broadly, all the statements we prove are always going to, in this argument, all statements are always about open sets. So any sufficiently small change always keeps us in the same open set. Any more questions? Okay, so we've removed the condition that xn should be in the starting set. But the next goal is to remove the condition on xn minus 1. We're going to do that with the same maneuver this time. So we again pick a time like vector t. It could be the same as before or a different one. And we're going to shift the pair of coordinates xn minus 1 and xn to xn minus 1 plus ut, xn plus ut. So now we look at w of u, say, which is chi inner product with 5x1 up to phi of xn minus 2, phi of xn minus 1 plus ut, phi of xn plus ut, where we're assuming for the moment that the first n minus 1 coordinates are in the region u, but no condition on xn. Well, we're going to make exactly the same argument as before. So w of u is 0 for small real u. Because small real u will leave xn minus 1 in the region it's supposed to be in, and there's anyway no condition on xn. Second fact is that w of u is holomorphic for mu positive. We prove that the same way as before. We write w of u we just insert e to the IHU to generate translations by u times t. The only difference is that now we're translating two operators by e to the IHU. But that doesn't affect the argument. We can still cancel the e to the minus IHU where it acts on the vacuum. And then, because h is bounded below by 0, e to the IHU is holomorphic in the upper half U plane. So that gives us this holomorphy. So, same argument as before shows that W of U is identically 0. And the next step is again the same. We pick a second time-like vector. And now we take xn minus 1 and xn to be shifted by both. And we again literally make the same arguments. I won't write, well, this is, if you're understanding the argument, you're getting tired of hearing the steps repeated. So I'm going to stop repeating it soon, but we next look at this function, k of u prime. And the same steps as before showed that it's identically 0 for all u prime. So in other words, the same steps as before. K of u prime is 0 for small real u prime. And it's holomorphic for imaginary part of u prime positive. For the same reasons. The first is because for small u prime, we don't violate the conditions under which we already know vanishing. And the second is because the Hamiltonian is bounded below by 0. But then, as before, shifting by arbitrary real coefficients in two time-like directions that are arbitrary lets us shift xn minus 1 anywhere. So now we know vanishing of our function with no condition on the last 2 points. We just need to know that the first n minus 2 points are in U. Now we keep going in exactly this way. So the next step would be to remove the condition. on, sorry, this is the xn over here. On xn minus 2, which we would do by shifting the last 3 points and then after shifting them in a time-like direction, we'd have to again shift them in another time-like direction, and that would remove the conditional on xn minus 2. Then we'd want to remove the conditional on xn minus 3. We'd repeat the process with shifts of the last 4 points in 2 independent time-like directions. And then we do it for xn minus 5 and so on until we get down to x1. So after the nth such step, we've proved the Riesz-Leiter theorem. That's 0 for all x1 up to xn. And therefore, as it's usually asserted, the states obtained by acting on the vacuum with field operators in the set U are dense. This is the usual statement of the theorem and the statement I gave originally. So we'll move on to discuss the interpretation of the theorem, but I'll stop again for questions about the proof. If you look in the book by Streeter and Witten, you'll see a proof that's sort of only a few sentences long. It doesn't have all these steps. Instead, he uses the edge of the wedge theorem, which is a theorem in n complex variables. I didn't like invoking the theorem because it's not very intuitive. And although the proof isn't that hard, to me, the proof is also not that intuitive. So I prefer breaking the proof of the theorem into all these steps, each of which was quite elementary, rather than invoking a slightly fancy theorem that we might not know much about. Okay, so no more questions on the proof? In that case, we're going to move on to the interpretation and the immediate question. Does it violate causality? If operator in U can create the moon far away. So we're going to first make sure that there's no conflict with causality. And after we've settled ourselves on that, we'll discuss more systematically what is the interpretation of the theorem. So here's the setup. Now we'll consider 2 open sets, an open set U and a faraway open set V that contains the moon. These are definitely space-like separated open sets. And then we'll write M for a moon operator. So we'll assume the moon operator has the property that its excitation value in the state chi is close to 1 if there exists a moon in region V, and otherwise the excitation value of chi is close to 0. So we can make such an operator in standard quantum field theory. We figure out what's the density and chemical composition and so on the moon. And then M is an operator that projects onto appropriate properties of these fields in region V. And so in particular, in the vacuum, the expectation value of the moon operator is close to 0. But Riech-Leiter says that there exists an operator O that lives entirely in region U, such that O acting on the vacuum is a state chi with a moon in region V. So in other words, Riech-Leiter tells us that there's an operator O such that in the state obtained by acting on the vacuum with O, the moon operator has an expectation value close to 1, although in the vacuum, its expectation is close to 0. Well, is this a contradiction? Well, the left-hand side is the same as O dagger M O. But we can assume that O dagger commutes with M because they're space-like separated. O and O dagger O and O dagger are supported in U, and the moon operator M. Gosh, what did I do? I did something I don't know how to do. The moon operator M is supported in region V. Those were space-like separated regions, as in this picture. So the two operators commute. So the left-hand side is the vacuum expectation value of M times O dagger L, which is close to 1, although the vacuum expectation value of M is close to 0. So is this a contradiction? Well, this is clearly a contradiction if O is unitary. Because then O dagger O is 1. But the Riech-Leiter theorem didn't say we can assume O to be unitary. It only said that there's some O. This argument actually proves that O can't be unitary. Now, given that O isn't unitary, all we found, you see, what do we learn from the fact that this 2-point function is 1, close to 1, but the expectation value is 0? What we've learned is that we've got a connected 2-point function. The vacuum expectation value of the product of these two operators, M and O dagger O, minus the product of 1-point functions, is close to 1 because the second term is close to 0 and the first term is close to 1. So we found a non-zero connected 2-point function between an operator in region U and an operator in the space-like separated region V. But that should be no surprise because we have correlators, vacuum correlators between space-like separated operators all the time. That's familiar. For example, in free field theory, Well, usually we define a field whose 1-point function is 0. So the 2-point function is the connected correlator. And we all know that the 2-point function is non-zero at space-like separation. So there's no contradiction with causality. There's nothing more exotic than the fact that correlation functions are non-zero in the vacuum at space-like separation. What this highlights, though, is that the naive idea that we can act on a quantum state with an operator is a little bit oversimplified.
Not bad, how about you?
Please mute. Please mute.
Edward, please, I muted all. Please unmute yourself so we can now hear you.
Okay, thank you. But we will want to unmute other people so they can ask questions. So okay, what this highlights is that the naive idea, we're accustomed to loosely saying, next we act on a quantum state with such and so an operator. But we're not actually able physically to act on a state of interest with an arbitrary operator. When we manipulate a quantum system, we do so by manipulating the Hamiltonian by which it evolves. And it's always evolving by a unitary operator. So we actually are only able to implement unitary operators. So in other words, if sitting here in the Milky Way, we were able to act on the state of the local quantum fields by an arbitrary operator, we could create the moon in Alpha Centauri, in Omega Centauri. Omega Centauri is a distant globular cluster. Alpha Centauri is just a star. So we're not able to act on a quantum state with any operator. We really act on a state with a unitary operator. When we think we're acting on the laboratory system with an operator that isn't unitary, what's actually happening is that there's a bigger system in which we've carried out a unitary operation. That's just because anything we do, anything that happens in the world in quantum field theory, whether it happens through our intervention or not, is unitary evolution, according to a Hamiltonian, which we think is time independent if you take into account everything. But in a simplified model where an experimenter is turning a knob, it's a time dependent Hamiltonian. So there's no contradiction with causality in the Rie-Schlieder theorem, but that fact might make you realize that your thinking about what you can do to a quantum system was a little bit cavalier. I think we should unmute people in case there's a question about that.
Okay, anyone can raise their hand also and I can unmute them. But I think people are hopefully free to unmute themselves.
Okay. All right, well, I don't see any questions. So in that case, we're going to go on. And before explaining the meaning of Rie-Schlieder, we'll discuss a corollary, an important corollary. So we have this open set U, which we assume is much less than the whole universe. That means it's space-like separated from another open set. So, let's say U might be here, and then U prime, which in this case would be on both sides. Well, in higher dimensions, U prime would be connected. But in 1 + 1 dimension in my picture, U prime would have 2 pieces. to the left and right of U. Anyway, U prime and U are space-like separated. And we can assume that they're maximal under that condition. In other words, starting with U, we let U prime consist of all points space-like separated from U. Then if we could have made U bigger, keeping it space-like separated from U prime, we might do so. And then we can assume that U consists of all points space-like separated from U prime. So usual way we get that state of affairs is that we take an initial value surface S, we split it into two pieces, which I'll call V and V prime. So S is V union V prime, except that V and V prime are open. So I should say that S is the closure of V union, the closure of V prime. And then we can let U be the domain of dependence of V, and U prime would be the domain of dependence of V prime. So this is an important setup where two sets are causal complements. That's one phrase that describes this. Now, we proved Riech-Leiter for U, but of course, U is any open set, so it also applies for U prime. And now the corollary that we want to prove is the following. Let A equal any operator in region U. Then A on the vacuum is non-zero. We'll prove that by using Riech-Leiter for U prime. Let B equal any operator. So A is any operator. If A is not itself zero, then A acting on the vacuum is not zero. Sorry. A few mistakes there. The more important one is that we want to prove that A on the vacuum is not zero. But we have to assume that A is not zero. The proof is a simple application of Riech-Leiter for U prime. Let B be any operator in U prime. If A annihilates the vacuum, then of course B on A on the vacuum is also zero. But A and B commute by causality, space-like separation. So A on B omega is zero. But Riech-Leiter says that the states of the form are dense. So A annihilates a dense set of states. And therefore A is zero. So what we prove by this simple argument is that if A annihilates the vacuum, and is space-like separated from region U prime, then A has to be identically 0. We simply argued that if A annihilates the vacuum, then it annihilates any state created on the vacuum by acting with something in region U prime. That's a dense set, so A has to vanish. So any question about the lemma or its proof? I should call it the corollary or its proof. So it's useful to introduce a little bit of jargon. Let A be the algebra of all operators in U, and A prime, or actually I'll call it B, the alg of all operators in U prime. Then we define a state omega is cyclic for algebra A if the states are dense and omega is separating if A omega being 0 for A in the algebra implies that A equals 0. So we've proved that in QFT, the vacuum is cyclic separating for U and for U prime.
Could I ask why it's called cyclic?
I don't know. Separating is more intuitive, I think, but it's the terminology cyclic is not very obvious. Only thing I can tell you for sure is that I didn't invent the terminology. It probably goes back to the 1960s, I think. Any other questions? So I said we proved that the vacuum is cyclic and separating for U and for U prime, but really for any open set. Well, any open set that's sufficiently small that it's space-like separated from another open set. The cyclic part didn't need the condition on space-like separated from another, but the separating does. Okay, now we're going to move on and try to understand the intuitive meaning of the theorem we've proved. And we're going to get an intuitive understanding. We'll see the intuitive understanding is oversimplified, but still very important. Oversimplified, but important. That the Rieschlieder theorem involves entanglements between degrees of freedom in and out of region U. We're going to suppose that the Hilbert space has a factorization of a tensor product of two Hilbert spaces, one describing degrees of freedom in U and the other describing degrees of freedom out of U. The other describing degrees of freedom in U prime. So this would be true in lattice gauge theory, in lattice scalar field theory. So we think of U and U prime as domains of dependence of two different parts of the initial value surface. So in Hamiltonian lattice gauge theory, we'd have latticeites in V, latticeites in V prime, and the fields in V would make up the Hilbert space HU, the fields in V prime would make up the Hilbert space HU prime. And we have a tensor factorization of the Hilbert space. We'll learn that that's not strictly true in quantum field theory. And we'll learn something about what's true instead. But we'll get some good intuition by imagining that this is true. Now, if we had such a factorization, then any state, such as the vacuum, would have a decomposition as a sum of tensor products of vectors in the two Hilbert spaces. Where I can assume the psi IU are orthonormal. And likewise, maybe I'll call these psi tildes, the psi tilde U prime. There may not be bases, as there may not be enough of them. For example, you could have a pure state, which would, with only one term in the sum, with only one term in the sum, it would certainly be the opposite of a basis. You could have any number of terms in the sum, or conceivably there are enough terms in the sum so that the psi IU and the psi tilde I U prime are bases of their respective Hilbert spaces. So, sorry, I have to take care of something in the house. Tesoro, please say yes. Yes, Gary. Yes, please. Yes. Sorry about that. So, okay. We have if we assume that the Hilbert space has a decomposition as a tensor product of states inside and states outside, then any state with the sum of tensor products of vectors in and vectors out. And now you'll see that if we let A be the algebra of all operators in region U, which would be all operators on the Hilbert space of states in region U, you can ask whether omega is cyclic or separating. And let's see, what do we find? So we find that if the psi tilde I u prime are a basis, if and only if they're a basis of HU prime, we find that omega is cyclic for A. We see that as follows. Any state chi, since we assume that the psi tilde i's are a basis, any state chi is the sum of some states alpha I tensor psi tilde I u prime, where alpha I are in HU. So if A in the algebra of operators on U has the property that A of the square root of pi psi iu is alpha I, then A on omega would be chi. And there's no trouble finding an operator A that will do that because these states are orthonormal. So there's no possible inconsistency. So therefore, with an assumed factorization, cyclic means that the psi tilde I u prime are a basis of HU tilde. Now, similarly, separating is equivalent to the psi iu being a basis of HU, because if omega is the sum of the square root of pi psi iu tensored with psi tilde iu prime, then the condition for A to annihilate the vacuum, if A is an operator on HU, it's the same as A annihilating all the psi iu's. A annihilates the vacuum if and only if it annihilates all the vectors that appear here. It can't do anything to these guys. They're linearly independent. So annihilating the vacuum is the same as annihilating all these guys. And that implies that A equals 0 if and only if the psi iu are a basis. So in other words, the vacuum is cyclic separating as proved by Riesleiter, for the algebra A on HU if and only if the psi IU are a basis and the other guys are a basis too. Well, we can state this in a perhaps more succinct way by looking at the density matrices. Maybe I should say the density matrices of the Hilbert spaces HU and HU prime. So if we have this state, the density matrices well, rho for region U is gotten by sort of integrating out or summing over the unobserved states in region U prime. It would be the sum of pi times psi IU, rho of region U prime would be the sum of pi times psi tilde IU prime, psi tilde IU prime. And now we can make a restatement. Another way to say the condition for cyclic separating is that rho U and rho U prime are invertible. So it means that all states in U are entangled with states in U prime and vice versa. So that's the intuitive meaning of Schlieder. The language that we've used in arriving at that intuitive interpretation is oversimplified, and that'll become clearer perhaps next week. But the intuition is that all states in U are entangled with states in U prime. So any questions here?
So what would change if we did not have like the same dimensionality of the Hilbert spaces? Or
Well, in ordinary, if the Hilbert spaces are finite dimensional so that your question makes sense, then cyclic, the argument shows that in finite dimensions, cyclic separating is only possible if the Hilbert spaces have the same dimension.
yeah, okay, I see.
The Schlieder theorem shows that in quantum field theory, the dimensions are infinite, of course, in quantum field theory. So your question doesn't precisely apply. But the Schlieder theorem shows that in quantum field theory, we always have something similar to quantum mechanics with the systems having the same dimension. But let me show you how what we couldn't get in quantum mechanics with systems having the same dimension. So you can have a quantum mechanical system with AB, and then if Schlieder applies, A and B are two quantum systems. They have Hilbert spaces HA and HB. If the two spaces have the same dimension, a state psi AB can have a non-degenerate density matrices. And then you would say that A and B can be fully entangled with each other. Now take A, B, C. Well, can A be, you see, one get out. In field theory, we can have three sets. Riech-Leader applies to any one of the three sets. We can't imitate that in quantum mechanics with a finite set of degrees of freedom. If you have finite dimensional Hilbert spaces HA, HB, and HC, to make Riech-Leader true for A, HA would have to have the same dimension as HB tensor HC. But you'd want the same thing for the other two cases.
Oh, yeah, okay, that makes sense.
So the quantum field theory does something that you can't imitate in quantum mechanics with finite dimensional Hilbert spaces. But the starting point of your question was correct. The situation, Riech-Leader is more similar to quantum theory, where A and B have Hilbert spaces of the same dimension, assuming those dimensions are finite, than if the Hilbert spaces are unequal dimension. Any other questions?
Well, about the factorization of the Hilbert spaces.
Yes.
So let's say we are in the gauge A not equals 0 and we apply Gauss's law. How do these type of constraints affect the
Well,
factorization?
I'll answer, there's no factorization in Hilbert space, even in scalar field theory. That's going to be something we'll discuss next week, but unfortunately not on Zoom, I'm sorry. So the discussion of the assumption of factorization was only to get an intuition about what Riech-Leader means. We'll also learn the limits of that intuition.
Thank you.
Sure. Any other questions?
So in this picture of U prime and U double prime,
Yes.
can I use operators with support on U prime to create identical states in U and U double prime? I have the idea that I shouldn't be able to do this.
Well, the theorem
Maybe
says-
it's just not a unitary operation.
Well, you haven't described precisely what you mean by identical states, but whatever the answer is, whatever you mean, the answer to your question will be yes. Because the Riech-Leader theorem says that operators in U prime can create anything.
Yeah.
More precisely, they can come arbitrarily close to creating anything.
Okay.
Whatever you want to create, the answer is yes, you can create it by operators just in U prime. It doesn't matter how small U prime is.
Okay.
If the theorem sounds strange, then you're understanding it correctly.
And this doesn't have any, I guess I have a vague recollection of this no cloning idea, and I'm not sure.
Well, we haven't stated what exactly no cloning means, but
Right. Okay.
if we state
Okay.
what it means, we'll see we're not contradicting it.
Okay. Okay.
You
So you
can't
think-
clone an unknown quantum state, but if you know what you're trying to create, you can create it, roughly. That's the problem with your question. The no cloning theorem refers to not a situation where you don't know what it is you're trying to create.
I see. Okay. Thank you.
Anyway, the no cloning theorem is definitely not applicable here. Any other questions?
So if the space is separated into three regions like U prime, U double prime, and U prime are far away from each other, they're separated by U double prime. Are they also entangled, all the states between them? Yeah, basically, I mean,
No,
there's-
I understand what you mean, and the answer to that question is no, but it takes a longer discussion.
I
So-
see.
In this situation,
Mhm.
it's possible. Well, we haven't even defined the right concepts for answering your question, but it's possible to have a state with no correlation between U and U prime.
I see.
It's actually explained in the last section of my, I think it's the last section of my lecture notes, the one that was recommended for today, called Some Entanglement Properties, blah, blah. I'm not going to explain it in these lectures, but you can find it in the written version.
I see. Thanks.
Any other questions? Okay, if there aren't any questions, I want to use the last 10 minutes, which I hope we still have, to explain why the ANAC is special. But first, classically, we have pointwise energy conditions. So in this course, we use the strong energy condition, which was that T00 minus a multiple of the trace was non-negative. We also used the null energy condition, which was that TUU is non-negative. U is a null vector, null direction. And then there's something that I don't think has a name, but so I'll call it the obvious energy condition. The T00 is non-negative. In each case, these are meant to be statements in each point and in each Lorentz frame. So all these conditions make sense classically. And the second and third are extremely well motivated. The first is less well motivated, but it's true in a lot of important theories like Maxwell's theory. But they're all false quantum mechanically. Well, they're all false quantum mechanically if you interpret them to mean, so let X be either T00 TUU or T00 minus the trace. I want to discuss the three cases together. They're all false if we interpret them to mean that in any quantum state, for all points P. In other words, if you take the classical statements, which all make sense and are important classically, and interpret them as statements that, so classically they're true in any classical solution. The analog of a classical solution is a quantum state. So the obvious quantum analog of these statements would be to say that in any quantum state, the expectation value of the operator X is positive. All those statements are false. To prove they're false, well, first of all, the vacuum expectation value of X is 0 by Lorentz invariance. Well, it's actually by Lorentz invariance and the fact that we've added a constant to the stress tensor so that the trace of the stress tensor, which is Lorentz invariant, has 0 expectation value. So in other words, once we define the energy so that the energy of the vacuum is 0, it then, with that condition, follows by Lorentz invariance that X of P has 0 vacuum expectation value. But X of P does not annihilate the vacuum. Well, one way you know that is that the 2-point function actually is singular. From your study of quantum field theory, you should know there are short distance singularities. And the short distance singularities certainly would not be possible if X of P annihilated the vacuum. But in today's lecture, we simply could say that Riesz-Leiter implies that X of P can't annihilate the vacuum because whatever P is, X of P is contained in some open set. And we prove that no operator supported in an open set, a proper open set small enough that it commutes with some other open set, can annihilate the vacuum. So therefore, there exists some state chi. Well, I could just let chi be, there exists some state chi such that chi is not orthogonal to X of P. Let me call this A. X of P on the vacuum isn't zero, so there's some state not orthogonal to it. For example, itself. I could just take chi to be this state. Now, look at X of P as a 2 by 2 matrix. In the space spanned by omega and chi. What does it look like? The upper left-hand element is 0 because the vacuum excitation value of X of P is 0. The upper right and lower left elements are A and A dagger, A and A bar, and this is something. The other element is some B. So A is not 0. So this matrix is not positive definite. So we've proved that there's some state with X of P less than 0. So just as a consequence of Riesch-Schlieder, we learned that
no carbon dioxide right now, but when that rock breaks through, it's going to start releasing carbon dioxide into the home. There's some, I can't give you a time when it's going to happen, but it's more than likely going to happen. So yeah, I'm going to
so we've learned that there can't be a pointwise condition on the energy in quantum field theory. It doesn't matter what kind of energy you want. Strong energy, null energy, or obvious energy. None of them can possibly be true in quantum field theory as pointwise conditions. Now you can ask, can you do better by smearing? In other words, take our open set U, which is small enough that Riesch-Schlieder is interesting. It's small enough so that it is space-like separated from something else. There's a U prime outside that's space-like separated. And let's smear over U. Let's call this XF. Can XF be equal to or greater than 0? Well, if you follow the arguments, you can see that the answer is no. But now we actually do need Riesch-Schlieder. For the fact that the pointwise operator didn't annihilate the vacuum, I felt you should know that because of your general knowledge of quantum field theory. It follows from the existence, for example, of a singularity in the 2-point function. But for the smeared guy, that an arbitrary smearing in a sufficiently small set that it's space-like separated from something else gives an operator that doesn't annihilate the vacuum. That's Riesch-Schlieder. So XF is, such an XF is not equal to or greater than 0. So we can't achieve positivity by any amount of smearing in an open set that's small enough that we're space-like separated from something else. But now we can look at the beauty of the ANAC. The ANAC says that if you have a complete null geodesic in Minkowski space, that the integral du of TUU is non-negative in all states. We'll actually give a proof of that later on. For now, I'm just asserting that it's true. But for now, we're going to see why we can't disprove it using Riesz-Leiter. The reason we can't disprove it is that space like separated, if we call the null geodesic gamma, space like separated from gamma is only a null plane. For example, suppose we take coordinates tz and x transverse in Minkowski space, and gamma is t equals z and x perp equals 0. Then you'll find that space like separated from gamma is only the set t equals z. Those are all the points that are space-like separated from a null geodesic, and they don't include an open set. So we can't invoke Riesz-Leiter to prove that the ANAC can't be true. That, of course, doesn't prove the ANAC, but it's part of the consistency of the story. So I'll stop here, and we'll continue next time. I'll just ask if there are any more questions. We'll continue next time in person, I'd like to stress.
Sorry, I have a quick question.
Yes.
This only says that you could take any of the operators, T00 or TUU or the T00 minus the trace and integrate it along the line, and that can still be positive. That
No.
by the
We can't disprove just using Riesz-Leiter that any one of those three might be positive.
right. Yeah, that's what I was asking. Yes.
Actually, the one that is positive is the null case TUU.
Yeah, I understand. Yeah, but
We eventually will prove it, but we haven't proved it.
okay, thanks. Yeah.
Sure. Any other questions? But what we have explained is that we can't rule out the ANAC from this point of view, and we can rule out all kinds of other things you might have hoped for. Nima? Go ahead if there's a question. Okay. I don't see any more questions, so maybe we should call it a day.